Salve, welcome to the amazing Tech Skill Hub course on beginner machine learning. This is lecture 8 and we will be exploring the wonders of unsupervised learning, which is a method in machine learning which is a part of AI. And this reminds me, why did the AI go to school? To improve its classification skills, of course. Ah yes, I cracked myself up. So let's get started, shall we? So everyone is asking these days, what is unsupervised learning? You will recall that we talked briefly about unsupervised learning way back in lecture 1. I know that may seem like eons ago, so let's revisit that lecture. In unsupervised learning, the model is trained on data without any labels. The algorithm seeks to identify patterns and relationships in the data independently. Unsupervised learning is often used for clustering, which is grouping similar data points together. So unlike supervised learning, where the model learns from input-output pairs, unsupervised learning focuses on finding hidden patterns or intrinsic structures in the input data. Unsupervised learning algorithms analyze and cluster data points based on their similarities and differences. The primary goal is to explore the underlying structure of the data, which can be useful for various applications such as data compression, anomaly detection, and exploratory data analysis. Here are some key characteristics. It's all about no-labeled data, which means unsupervised learning does not require labeled datasets. The model learns from the raw input data. Also, pattern discovery. So the main objective is to identify patterns, groupings, or structures within the data. And finally, dimensionality reduction, often used to reduce the number of features in a dataset while preserving essential information. Well, now that we are getting to know our unsupervised friend, let's talk about some common techniques in unsupervised learning. Let's dive deeper into clustering. Clustering is the process of using algorithms that group a set of objects in such a way that objects in the same group, or cluster, are more similar to each other than to those in other groups. It's like a computer-fast game of matching. Some popular clustering algorithms include k-means clustering. This partitions the data into k distinct clusters based on distance to the centroid of each cluster. Here is how this works. First, the algorithm randomly selects a number of centroids or cluster centers. Next, each data point is assigned to the nearest centroid. Then the centroids are recalculated based on the new groupings, and the process is repeated until the clusters are satisfactory. K-means is especially useful in things like market segmentation by dividing customers into groups based on similar behaviors and preferences. And also image segmentation by grouping similar images into clusters K-means is limited because it can be sensitive to outliers. Outliers can distort the clustering process and make the clusters less reliable. Also, it can be difficult to determine the right number of clusters, so that is K-means. And there is hierarchical clustering, which builds a hierarchy of clusters either through agglomerative bottom-up or divisive top-down approaches. First, you start with each data point as its own cluster. Then you calculate the distance between all data points. Next, find the two closest data points or clusters. Then merge the two closest data points or clusters into one cluster, and you repeat steps 2 to 4 until all data points are in one cluster. What's cool about hierarchical clustering is it can visualize the hierarchy of clusters. It doesn't require knowing the number of clusters in advance, and also it can handle different types of data. However, it can be computationally expensive for large datasets. Said better, it takes a lot of time and computer power. Also, it may not be suitable for high-dimensional data. That is hierarchical clustering. Finally, another algorithm is db-scan, or density-based spatial clustering of applications with noise. That's quite a mouthful, isn't it? db-scan groups together points that are closely packed together while marking points in low-density regions as outliers. Two important points in db-scan are epsilon, which is the radius of a circle, and min points, which are the minimum number of points a point must have, including itself, in order to called as a core point. Here min point is 4, so we must have 4 points to be a core point. You can that the green point has more than 4 points in its neighbourhood, including itself. so it is called a core point. The point which does not have minimum number of points, but is a neighbour of core point, is called border point. Here, the blue point is a border point. The point which does not have minimum number of points and is not a part of a core point is called noise point. Here, the orange point is a noise point. If two or more core points are neighbour of one another, then they form same cluster. DB scan. That's a solid overview of clustering. Another technique is dimensionality reduction. Dimensionality reduction techniques aim to reduce the number of features in a dataset while retaining its essential characteristics. This is particularly useful for visualizing high-dimensional data. Remember, high-dimensional data in machine learning is a dataset with a large number of features or variables. This data can be difficult to work with because of its size and complexity. Like complex hospital data, that can have a ton of variables. Dimensionality reduction is good because it improves computational efficiency by working with smaller datasets. It can enhance model performance by preventing overfitting, and it enables better data visualization by reducing dimensions to 2D or 3D. There are some common methods, like principal component analysis, PCA, which reduces the dimensionality of a dataset by identifying the most significant features, called principal components, within the data, allowing for easier visualization and analysis while preserving as much relevant information as possible. Essentially, it simplifies complex data into a lower dimensional space by finding patterns and removing redundancy among features, and here is a slobber knocker. T-distributed stochastic neighbour embedding, also called T-SNE for people who are not fans of 3-minute-long titles. It is used to visualize high-dimensional data by projecting it into a lower dimensional space, typically 2D or 3D, while preserving the local relationships between data points. T-SNE calculates the probability of each data point being close to its neighbours in the high-dimensional space, then attempts to replicate these relationships in the low-dimensional space, symbase, by adjusting the positions of points to minimize the difference between the two probability distributions. The T in T-SNE refers to the student's T-distribution, which is used to model the probability of points being close together in the low-dimensional space, allowing T-SNE to better capture local structure compared to other dimensionality reduction methods. There are also autoencoders used in dimensionality reduction. These are neural networks designed to learn efficient representations of data, typically for the purpose of dimensionality reduction. This is a neural network architecture with an imposed bottleneck in the network, which forces a compressed knowledge representation of the original input. So after clustering and dimensionality reduction, let's consider anomaly detection. Anomaly detection involves sending little nano spies to detect those sneaky anomalies, right? No, huh? Oh well, I try. Anomaly detection is the process of using machine learning algorithms to identify data points that significantly deviate from the expected pattern within a dataset, essentially flagging unusual or anomalous observations that might indicate problems or irregularities within the data. The way anomaly detection works is by identifying rare items, events, or observations that raise suspicions by differing significantly from the majority of the data. Some of the techniques include isolation forest. This is an ensemble method that isolates anomalies instead of profiling normal data points, or perhaps one-class SVM. This is a variation of the support vector machine that is trained only on the normal data to identify outliers. So those are some anomaly detection techniques, and that is the end of our discussion on some techniques we use in unsupervised learning. So we have explored the meaning of supervised learning and talked a bit about the ways it can be done. So why would we use it? What are some of the applications of unsupervised learning? Unsupervised learning has a wide range of applications across various fields. We mentioned market segmentation. Businesses can use clustering to identify distinct customer segments for targeted marketing. And we have image compression. Dimensionality reduction techniques can help compress images while preserving quality. And there are recommendation systems, and unsupervised learning can help identify patterns in user behavior to suggest products or content. Finally, genomics. Yeah, funny word that. Genomics. Clustering techniques are used to group similar genes or proteins based on expression data. While unsupervised learning offers powerful tools for data analysis, it also comes with challenges. How about interpretability? That is actually a tough word to say. Anyway, interpretability means the results of unsupervised learning can be difficult to interpret, as there are no labels to guide the understanding of the clusters or patterns. And it is not easy to choose the right algorithm, with many available algorithms. Selecting the most appropriate one for a specific dataset can be challenging. Scalability might also be a problem. Some algorithms may not scale well with large datasets, leading to performance issues. To summarize, unsupervised learning is a powerful tool for discovering hidden patterns in unlabeled data. Clustering, dimensionality reduction, and anomaly detection are key techniques, and they allow us to group similar data points together and visualize the data in useful ways. As you continue your journey in machine learning, remember that unsupervised learning is all about exploration and discovery. It's like being an explorer in a vast, uncharted territory. You never know what patterns you might uncover. It is a vital area of machine learning that enables the discovery of hidden patterns in data without the need for labeled examples. As the field continues to evolve, the potential applications and methodologies for unsupervised learning will expand, offering even more opportunities for innovation and discovery. Well, that's all for today. Cheers and have a blessed day. Like and subscribe for the sake of Tech Skills Hub and for my vocal cords, because I've been chit-chatting in these videos a lot. I need some tea with honey. This is Ethan signing off.